In this video, we're going to do an overview of capacitors, so the rest of chapter 26 here. Capacitors are circuit elements. This is the first circuit element that we're going to see other than the battery that we introduced last video. And the purpose of a capacitor is to store energy by separating charges. So capacitor, the definition of a capacitor is just two conductors. That's it. So anytime you have two pieces of metal in space in some particular separation, particular orientation, as long as those are fixed, then that's a capacitor. You're changing the capacitor as you change the distance between them or like the orientation between them, but fixing those two things, that's a certain capacitor. And as we start to move charges from one to another, so there's a charge separation that's created. We label the magnitude of the charge on the capacitor Q. So what that means, if a capacitor is charged to charge Q, it means one of the two plates, one of the two pieces of metal, one of the two conductors or electrodes, one of them has positive charge, one of them has negative charge, and we label the magnitude or the absolute value of that charge Q. So by definition, positive. There's a potential difference that's set up between the two conductors. You can take any point, remember that a conductor is an equipotential. So if you take any point on here and any point on here, it's the same delta V. So you can integrate along this electric field. If we're integrating this way with the electric field, then there's a decrease in electric potential, but it has some magnitude delta V. So by definition, this is the positive absolute value of the delta V between them. Well defined because one of them has a certain value, a constant value of electric potential. The other one has a different value of potential. So this is some well-defined thing. By definition, positive for this ratio. So delta V is proportional to Q, the charge of the capacitor. And so when you take this ratio actually is independent of Q, because delta V is proportional to Q. This constant of proportionality relating these is the capacitance. So maybe a better way of writing this is this way, because this emphasizes that C is the constant of proportionality that relates the charge and the potential difference between them. So this is the definition of the capacitance C of a capacitor. It has SI units of coulombs per volt, or we give that a name, and that's farads. So a farad is defined to be 1 coulomb divided by 1 volt. So farad labeled capital F. When we talk about capacitor, it has some capacitance in farads. And it's basically like how much, so if you look at this, the bigger C is, so imagine you hooked up a 1.5 volt battery charging capacitor. How would you do it? I'll go back to that other screen in a second. But the way you would charge up a capacitor would be to take a battery, take a piece of wire and just connect the positive terminal to one electrode or one conductor, one of the plates, one of the conductors that comprise the capacitor, and take another wire and connect it to the negative one. So you set up a potential difference 1.5 volts if the battery is 1.5 volts. So imagine that's fixed. Like you're not going to swap out the battery for anything else, but that's fixed there. This formula right here is telling us that for a given potential difference, the bigger the capacitance of the capacitor, the more charge it can hold. Okay, so you could have two different capacitors, two pieces of metal and then two much bigger pieces of metal separated by the same distance. You can actually store more charge on the bigger one. And so if you hook them both up to a 1.5 volt battery, there will be more charge on the one with a bigger capacitance, right? Just based on this formula. So it's like how much charge. So for a given potential difference, the bigger the capacitance of a capacitor, the more charge it can hold. Right? The most famous kind of capacitor that we need to be familiar with is the parallel plate capacitor. So this is if you have two plates separated by some distance that's very small compared to the other two dimensions. And the area of each of these is A. So you assume there's some charge Q, you find that potential difference, you take the ratio, and you'll find that the capacitance is proportional to the area divided by the distance separating them. So it makes sense that it's proportional to area, right? The more area, the more charge it can store. What's maybe more surprising is that the closer they are together, the more charge you can store on it. And I want to emphasize what the book says, that this is a geometric property, right? It only depends on the area of the plates and how far you're separating them. but nothing else, right? It doesn't depend on the charge that you're putting on it or what battery you're hooking it up to. So it's a purely geometric property, and that's in general true for any capacitor. We can modify it by maybe like sticking some, maybe we stick some plastic in between here. That would modify the capacitance of the capacitor, but we'll talk about that later when we talk about dielectrics. Okay, so this example is just playing with some of the parameters for a parallel plate capacitor. So just getting used to that formula. The next part of this is combinations of capacitors. So this will be especially useful when we talk about circuits, but we want to know how we can, if we combine more than one capacitor together, we want to know how they act. And it turns out there are some rules for if you combine capacitors this way and this way. There's some rules for finding the equivalent capacitance. So in other words, as long as you're looking outside this region, these three capacitors together just act the same as if you had one single capacitor with some equivalent capacitance. So if you know the values of C1, C2, and C3, which are the capacitances of those three capacitors, there's some formula that will let you just treat all three of those things as one object called the equivalent capacitor with its own equivalent capacitance. So the next part of the book derives formulas for two different types of combinations. So we need to know what the types of combinations are. And the two words are parallel and series. Oops, that's not, and this one is series. So parallel versus series combinations of capacitors. So there's some rules for this. Okay, so series is probably, it looks like it's a little easier, right? So series combination is you have a capacitor, and this is the circuit symbol for a capacitor. You know, it's two lines that are the same length. So be careful, because later we're going to talk about batteries where if the lines are different lengths. So really try your best when you're doing your written work. This is a battery, different lengths, right? And we use the negative terminal for the smaller one, the positive terminal is the longer line, and the negative terminal is the smaller one. And a capacitor has equal lengths for those two things. So you really got to, so a lot of times students will do something like, you know, something that's exactly like halfway between them. I can't really tell a lot of times. So just exaggerate. Okay, so if you have so how do you tell if two are in series or in parallel? Well, series is easier. Series is you have a capacitor, and without the wire branching off and connecting to something else right here, if you go straight from one capacitor straight to another capacitor with no branching off at all, then those two capacitors are in series. Right? So see how they're just right in a row and there's no branching off of wires in between them or anything. So if that's true, you have a series combination of two circuit elements. Really, this is more general than capacitors. So if you have a battery like this and a battery like this, and there's no branching off of a wire right here, then those two batteries would be connected in series. These three capacitors are all connected in series. For a parallel combination, the rule is a wire, if a wire splits, it hits one circuit element on one side and one on another side, and then the wire comes back together, and then you're able to connect the opposite side of both of those two circuit elements together with just wires. If you're able to take your finger and just go through wires to the other one, then those two circuit elements are connected in parallel. So here we're touching one side of the capacitor here, and then from this point we're touching these two sides of those two objects. And so C1 and C2 are in parallel right here. And then the same thing is true for C1 and C3. So actually all three of these things are connected in parallel. So those are the rules for seeing if two things are connected either in series or in parallel. If you have two capacitors or any number of capacitors in parallel, this is how you find the equivalent capacitance. And if you have any number of capacitors in series, you have this formula, which is a little more complicated. Right? So this is called, you know, this is called adding harmonically versus just adding up the capacitances. You'll notice that parallel, if the point is, if you're combining capacitors because you want as big a capacitance as possible, you want to combine them in parallel. Because this formula right here has, for series combination only, C equivalent is less than CI for any I, for all I. So the capacitance will go down if you connect them in series. So like right here, this equivalent capacitance is less than C1, and it's also less than C2. And then numerical example of, so if we were to simplify this circuit diagram, we would have to combine these two first, right? You'll notice that C1 and C2 are not in series and they're not in parallel. So you can't start by combining those two things. You have to start with these two. C2 and C3 are connected in parallel. And then after you combine those two, that equivalent capacitor is in series with C1. So this chapter gives you some practice in combining series versus parallel combinations of circuit elements. Energy stored in a capacitor. We have two important formulas for the energy stored in a capacitor. So energy stored in capacitor U is 1/2 CV squared, or U equals Q squared over 2C. So which one you want to use depends on what you know about the capacitor. Do you know the potential difference across the capacitor, or do you know the charge on the capacitor? Do you know V or do you know Q? So for example, if pretend you have a problem where you have the capacitor always hooked up to a battery. That means you always know what the potential difference is. So if I had a capacitor hooked up to a battery and I start decreasing the distance between the two parallel plates, if we have a parallel plate capacitor, I'm increasing the capacitance in that case. So I would focus on this one because I know the delta V would be constant and equal to the potential difference of the battery. The V would be constant, so I would use this, and the capacitance would go up if I was bringing the plates closer together, and the stored energy would go up. Right? But if I had a capacitor that wasn't connected to a battery, it's isolated, and the charge can't change. So if that's the case, I would look at this one where Q is constant. So I have a capacitor with some charge not connected to a battery. I bring the plates closer together. I increase the capacitance. But that means I'm decreasing the stored energy. And the reason that happens is that the plates basically want to fall into each other anyway, right? If one's positive, one's negative, they're attracted to each other. And so the stored energy will go down in that case. Right? So whether the stored energy goes up or goes down as a result of some change depends on what's going on in the problem. So both of these are useful depending on the circumstances. And SI units. So as long as capacitance is in farads, V is in volts, Q is in coulombs, you're going to get a joules, number of joules out of here. In general, the capacitance, like a 1 farad capacitor is a huge capacitance. And any capacitor that you're dealing with for household item circuitry is like not even millifarad, but like microfarad or nanofarad, maybe even picofarad for small things. So you tend to deal with small capacitances, small energies for these things. Maybe a defibrillator has a bigger one. Maybe that one's millifarads, or probably not even farad though. Farad's pretty big, huge. So what's going on? The reason, so one way of thinking about where the energy is stored is that it's stored in the electric field. So if you have a positive and a negative plate here, there's an electric field that's going from the positive to the negative plate. So another way of thinking about the energy storage is that it's in the electric field. So one formula is that the energy density, the energy per unit volume, which is given by this formula. So this tells you that if you have some chunk of space which has some electric field, so volume V, you could take your energy density times the volume. So energy density is lowercase u times E, or U subscript E. So energy density times volume, energy density times volume equals energy stored. So be careful, the capital U versus lowercase u are different things. All right, one last topic is dielectrics. A dielectric just means an insulator, but it changes the properties of the capacitor somewhat. So if you stick a dielectric totally in between the space right here, you're not changing the fact that you still have two conducting surfaces, right? So you can still do everything we talked about before still applies. But the dielectric will polarize because of the presence of the electric field, and that changes the properties of the capacitor. And a key property is that when you insert a dielectric, you always increase the capacitance of the capacitor. So notice how whatever capacitance you start off with, C naught, the capacitance goes up as a result. Okay. So capacitor with a dielectric inserted has a bigger capacitance. And your book talks about, well, why this is. It's because you're screening the electric field. So basically the electric field will go, it will be modified because of this. It polarizes, so you can keep piling up charges here. That's basically the gist of what's going on. So we tend to label dielectrics, or insulators, using a factor by which it will increase the capacitance of a capacitor. This is called the dielectric constant kappa. So a piece of paper, imagine you have a dielectric, two pieces of metal, and you want them as close as possible, but they can't touch, right? Or else it would just be one conductor. So you have a piece of paper in between them. Well, that piece of paper is going to modify the capacitance of the capacitor by a factor of 3.7, which is a good thing if you're trying to increase the capacitance as much as possible. So other formulas, like what happens with the energy when you insert the dielectric, well, that depends on whether it's hooked up to a battery or isolated. So you have to use some of the, which formula is useful will depend on the setup of the problem. So this is just some examples. And then the final example here is a cylindrical capacitor. So you don't have to have parallel plate capacitors. In general, you just assume the charges are Q and minus Q. All the work is in finding the delta V. And at the very end, you can take the ratio of Q versus V to find the capacitance. And for a cylindrical shell capacitor, you have to do capacitance per unit length because really it's infinitely long. And that's it. So the example we have here, I don't want to go too long, but you can at least do part A. I guess we might as well finish. If you've gotten this far, you probably want to know how to do the problem. A. So stop the video and think about, well, what two capacitors are either in series or in parallel? There's one place you have to start here. So you have to start by combining these two. So you have two capacitors in parallel. And if it's C and C, this is equivalent to a single capacitor C prime equal to 2C. Remember, the formula for combining capacitors in parallel is that you can just add up all the capacitances. Right, so we'll call that C prime. So then, after we replace those two with C prime, we have, so then the next step is that we have this capacitor, this starred capacitor, C, combined with C prime, which is equal to 2C. Those are connected in series. And this is the same as, we'll call it C double prime. And there's a formula for this, and this is the more complicated formula if you're combining capacitors in series. So 1 over C double prime is 1 over C plus 1 over C prime, or 1 over C plus 1 over 2C. So 1 plus 1/2 is 3 halves. And inverting this, we get C double prime is 2/3 times C. So overall then, this circuit, let's go back up here. We have a 1.5 volt battery with the positive terminal on the left side. So one way that we can do this is this 1.5 volt battery. And it's connected to a single, effectively, this is connected to a single capacitor with capacitance 2/3 times whatever that value is, C. So that's part A. Find the equivalent capacitance, it's 2/3 C. Find the charge on the leftmost capacitor, the one with the star. Okay, so so for part B, we have to, so we've combined everything to the equivalent capacitance of the capacitor. I'm just going to call this is V, is 1.5 volts. So it's kind of weird that we were given the number for the battery, but we weren't given a value for C. So I'm just going to have a symbolic answer where V is 1.5 volts and C is whatever value it takes on. So our answer will be in terms of C and V. the reason we can combine the reason we want to combine all the capacitors and do an equivalent one is that we know the potential difference across the plates of this capacitor is 1.5 volts. So the charge on the C double prime, so we'll call it Q double prime. This is the charge on the equivalent capacitor, is C times V. So this is 2/3 CV. So that's the charge that's stored on that thing. And then we work back, then we start looking backwards and we say, well, the charge, so really C double prime is these two things connected in series. And for two capacitors connected in series, they have the same charge. So really the charge of this one is the same as this one, and they're equal to the same charge as the overall capacitor, overall equivalent capacitor. They don't have the same voltages, right? The voltage difference across here is the sum of the voltage difference here and the voltage difference here. So we can't make this statement about the delta V's, but we can for the Q's. And one way of thinking of this is, well, whatever charge this sets up. So by the way, I'm imagining a Kirchhoff loop here. So if I'm with my finger, I'm starting right here and I'm starting to think going across here. So I gain voltage. That means I need to lose voltage across the capacitor when I go back to our starting point. So that tells me that the this side is going to be positive and this side is going to be negative. So whatever charge, so this is positive, this is negative. This center island is exactly that. It's like an island. So imagine we're just looking at this conductor right here, all that metal connected. It's overall neutral. That doesn't have a net charge right there. So whatever negative charge is on the right side of this capacitor, there's a positive charge on the other side, on the left side of this one. So this is sort of explaining why the charges are equal for two capacitors in series. And in particular, they have, those are the sides where it's positive and negative for this particular, hooking it up in this way. So overall, the question for part B, find the charge on the leftmost capacitor. Well, it's the same as the charge of the overall equivalent capacitor. So this is also the charge on the C star, this red star, this one right here. Okay, so the answer is this right here for the charge, and then this was the equivalent capacitance for part A. All right.